Hey everyone, our first mini lecture today will be about force vectors, vector operations, and addition of coplanar forces. Now I want you to look at this image and you can see two different chains, chain A and B, pulling onto one hook, hook C. So how do we calculate the resultant forces on the hook to make sure that it doesn't break, which is our job as engineers? This is an important application on vectors. Now, for first mini lecture objectives, students will be able to resolve a 2D vector into its components and add 2D vectors using Cartesian vector notations. So, first of all, I'd like to share the difference between scalars and vectors. Example of a scalars are the mass and the volume, and examples of vectors are the force and velocity. The characteristics of scalars is that they have a magnitude only, either positive or negative. As for vectors, they have a magnitude and direction. Now, an additional rule, scalars are simply added together by arithmetic, and the addition of vectors requires parallelogram law. And from now on, we're going to be writing vectors into a special notations. Either in a bold font or a line or an arrow above them. Now, vector additions can be done either by using the parallelogram law, okay, which you can see in this figure. We have vector A plus vector B. The resultant vector is shown here using parallelogram law. Or you can use the triangular method, which is always tip to tail. So basically, if we want vector A plus B, we use the tip of vector A and attach it to the tail of vector B. Same thing, if we want vector B plus A, we have to attach the tip of vector B to the tail of vector A. So it's always basically tip to tail. This is the triangular method of adding vectors. Now, I'd like you guys to think about this question for a couple of minutes. So how do you think we subtract a vector? And how do you add more than two concurrent vectors graphically or using the triangular method? I'd like you all to share your thoughts on our discussion board online. So I'll set that up on e-learning. Now, there are a couple of rules I would like you guys to remember in order to use in vector additions. Our first rule is sign law. Basically, as you can see in this triangle, we know that A small over sine A is equal to B small over sine B and is equal to C small over sine C. Our second rule is cosine law. So we know that A small squared is equal to B squared plus C squared minus 2bc cosine A, okay? And the first step towards vector addition is the resolution of a vector. So resolution of a vector is basically breaking up a vector into its components. So it's kind of like using the parallelogram law in reverse. If we have a resultant vector like R, okay, we break it down into its components on the B and A axes. So it's kind of the reverse of parallelogram law, where we had vector A plus B, and we got the resultant force R. So Cartesian vector notations, we're going to learn how to break down these vectors on the x, y axes. For example, if we have this F vector, we want to break it down to its x-axis components, or I, we're going to call it from now on, and break down its component onto the y-axis, or call it j from now on. The first step is we resolve vectors into the components using the x and y-axis system. Then each component of the vector is shown as a magnitude and a direction. The directions are based on the x and y axes. We use unit vectors I and j to designate the x and y axes. So basically from now on, we're going to call these unit vectors, instead of x and y axes, I and j unit vectors. Now, As you can see in this example, we have the vector f, and we break it down to its components fx on the x-axis, or y-axis, as I said, we're going to call it from now on. And we break down the component to the y-axis or j-axis. So f is equal to fxi plus fyj. Another example is f hat, breaking down to its x-axis component, or I, and y-axis component in negative j. Now the x and y-axes are always perpendicular to each other, and together they can be directed at any inclination. So, in conclusion, additional of several vectors, we use these steps to add them together. Step 1 is to resolve each force into its basic components, okay? Step 2 is to add all the x components together and add all the y components together. These two totals become the resultant vector. And step 3 is to find the magnitude and angle of the resultant force. So, as you can see in this image, we have three vectors, f1, f2, f3, okay? f1, we break it down to its x and y components. f2, same thing, break it down to its x and y components. And f3, we break it down to its x and y components. After that, we add these vectors together. So f1 plus f2 plus f3 is basically, as I said, we break it down to its I and j components for each vector, and adding all the I components together to get a resultant vector I component, and adding all the j components together to get a resultant j component for the resultant vector. After that, we get the magnitude of the resultant vector by using this equation, the square root of frx squared plus fry squared, and the angle of the vector is tan inverse fry over fx. So basically, we can represent any 2D resultant vector with a magnitude and angle as shown in this figure. Now, I've added a group problem solving. So I'm going to break you guys up into groups, and I want each group to try and solve this problem together. Basically, we have three concurrent forces acting on this bracket. The magnitude, I want you to find the magnitude and angle of the resultant force of all these three forces. And I'd like you guys to solve this problem by using a step-by-step plan. In this plan, I want you to resolve the forces to their x and y component, each force, f1, f2, and 3. Then add the respective components to get the resultant vectors together, and then find the magnitude and angle of the resultant components. That's basically the end of our first mini lecture. I'll see you guys next time.